for coming to the next installment of our research rounds. I sort of drew the short straw to give this one, so I thought I'd unpack a puzzle that I've been intrigued about for actually quite a few years, but where recently I think the field is moving quite substantially and is now getting to a point where this is becoming to play, getting to a point where it's relevant for clinical practice rather than just an immunological puzzle. So the talk I've given this regulatory T cells and immunotherapy, time to take them seriously. So it's really more a reflection on the field and my personal take on our own data and how I would like to take this problem forward to further clinical investigation. And I would really like to give this about 30 minutes or so, 35 minutes perhaps of the presentation, and then really interested to hear what everybody thinks and try and take this into the conversation. So chemotherapy or cancer immunotherapy is really an intriguing puzzle, and the key starting point is that, of course, cancer has developed, so the immune system must have failed. So then the question is, can you turn this failure around? And if you turn it positively, can we re-establish immune control? And if that is theoretically possible, what does immune control look like? And I think there are a number of sort of levels at which you can look at this. First of all, of course, we can see if we are successful, then the cancer disappears. But the sort of cellular or immunological correlates of this are still hotly contested and subject to many papers. Tens of thousands of papers have now examined this question with varying degrees of insight. So if we can actually understand what at a cellular level immune control means, then can we turn this into something we can affect? Can we get there by making choices and using treatments? And the armamentarium that we have is rapidly expanding, but of course checkpoint inhibitors are the backbone of all of this, and I think that vaccines as a model to train immune cells in a specific way will play a very major role in our armamentarium going forward. So the issue really is one between immunosuppression and immune control. And if immunosuppression wins, and that's of course what happens when we don't treat the patient or when our treatment fail, and then the net effect is tumor growth. And we know that there are some cellular counterparts to this lack of control or tumor growth. So one bit, of course, is what do the tumor cells bring to the table, but we now know that within the tumor microenvironment, there's a whole host of cells that will contribute to that bad outcome, and particularly regulatory cells or myeloid cells, including neutrophils, as well as the fibroblasts, play a major role. If, on the other hand, we achieve immune control, then we know that the key correlate for protection is the induction of CD8 positive T cells that have cytotoxic function, and they remove the tumor. Although, again, this is changing more recently as we're beginning to understand that not just cytotoxic CD8 positive T cells, but CD4 positive T cells, as well as natural killer cells, can actually contribute to this control. And I use this slide a lot, mainly because it sort of reflects my first really aha experience in clinical practice. This was a gentleman with metastatic non-small cell lung cancer with a relatively small primary, but widely metastatic disease. And he was treated with checkpoint inhibitor chemotherapy and immunotherapy and remained disease-free until he died of other reasons, COVID-related, about 6 years later. So the message really is that even in really bad cancer, there is a possibility that we can alter and profoundly reset the immune system in that patient to eliminate malignancy. So I think by all measures that I could levy, at least, this patient had achieved a durable complete response and I think was probably cured from his cancer. Now, if we then think about what is necessary for this kind of outcome to happen, then we don't know all the parties, but we know that some parties are really well described. And at the heart of all of this is really the interaction between a T cell and the tumor cell. So here's our T cell at the bottom, and it's this is the lines are the membranes of the, in this case, the T cell. And there's a whole bunch of sticky out stuff on the surface of the T cells. These don't really coexist usually, but they're the T cell receptor, that is the sort of nose of the sniffer dog that the T cells represent. And they recognize a small chunk of protein called a peptide that is found on cells, all cells in our body, but particularly the training occurs through a set of cells that are called antigen presenting cells. And these are born, and their main remit in life is to present peptides in the MHC molecules to the T cells, and specifically through the T cell receptor. And this T cell receptor can then be associated with the second molecule, which is CD8, and I've already mentioned that, or alternatively with the CD4 molecule. And depending on what this associate molecule is in a particular T cell, the T cell receptor will bind peptides that are either found on MHC class 2 or MHC class 1 molecules. Now, the important bit is that this T cell receptor is really highly specific. And if you take two random T cells out of one human being or out of multiple human beings, then their T cell receptors are all subtly different. And this subtle difference identifies the ability, or mediates the ability, to find and recognize particular peptides. And the all cells in our body, all nucleated cells, that is, make this MHC class 1. And that's why we think that the CD8 T cells are the key correlates for protection, both against infection as well as in cancer. But under the right circumstances, many cells in our body also can upregulate this MHC class 2, and particularly in infection or indeed in cancer, the tumor cells or other cells in the body upregulate MHC class 2 and then become susceptible or visible to CD4 T cells also. So this is the sort of backbone of how we protect ourselves against bacteria, viruses, parasites, but also against cancers. And the secondary or the CD4 positive T cells are the sort of parallel backup strand that is also needed for intact immune responses. Now, the easiest correlate, and I think I've already shown this slide in a number of presentations, is to work out how well this works by simply counting T cells. So here are our nests of adenocarcinoma, in this case from lung cancer, and in between are all these purple dots that are T cells. And you can see that they're sort of lying between the tumor cell nests. Here, the red cells are some erythrocytes in some blood vessels. And if these T cells now get into contact with the tumor cells, they have a chance to engage with them through this MHC T cell receptor interaction. And if you have the right kind of T cells, they will eat the T cells by making holes in the membrane and then blow up the cells through chemicals such as granzymes that are like little hand grenades that the T cells release onto the inside of the tumor cells. And if that is successful, then the tumor is controlled and the patient survives. And if that's unsuccessful, then what happens is that the patient, of course, dies from the malignancy. Now, one of the puzzles is that we don't really know what these T cells actually recognize. And if we look at the list of potential targets that might make cancer cells different to healthy cells, then the list is actually quite long. So I've listed here categories of molecules that might be different between tumor cells and healthy cells. And now that I'm working in head and neck cancer, of course, a viral antigen, so human papillomavirus, is a really intriguing target because that's found on the cancer cells, but there is no healthy structure in our body that makes the virus, so human papillomavirus in this instance. So you would have thought that that is a really good target for training and training immune cells. And indeed, a number of lines of evidence suggest that that is a really good idea, because if you look at all HPV-driven cancers as opposed to those that do not have HPV, then these tumors often do much better, no doubt reflecting the fact that these viral antigens are visible to the immune system. There is also a whole bunch of non-viral antigens, and the most widely recognized non-viral antigens that we are interested in immunotherapy are these neoantigens. They're the ones that are the result of the genetic activity that makes cancer cells abnormal in the first place. And if you have mutations in the genome of the tumor cells, then some of these mutations can be visible to T cells, mainly again MHC class 1, but also to CD4 T cells through MHC class 2. And there is now a growing body of evidence that these play a major role in immune control that is naturally occurring, as I've demonstrated here. But there's a number of other antigens, some of which have been successfully, most of which have not been so successfully evaluated in early phase clinical trials. So some of molecules that are not found in healthy cells but are upregulated in tumor cells are the cancer testis antigen family, and our own interest is in one of the MAGE family antigens, or molecules that are actually also found in healthy cells, such as CEA, for example, but that are highly upregulated and therefore differentially expressed in tumor cells. And again, we're targeting examples of these through our own vaccine program. And of course, then there are some molecules that are really intriguing because a molecule like PSMA, or prostate-specific membrane antigen, is found on tumor cells only in prostate cancer, but is found on the non-malignant neovasculature that the cancer trains the body to make to feed itself in many solid tumors. So then it becomes a molecule that is differentially expressed in the non-malignant cells in the tumor, but a critical feature of the malignant process, because PSMA is not found on healthy neovasculature. So the difficulty in all of this is that the number of antigens is large, and we don't really know what the best antigen is and how to pick one for intervention, for example, to vaccination. And all of these are being tested in parallel in clinical trials. We know some things, however, and we know that they're not all created equal. So if we ask about how similar these targets are between healthy cells and tumor cells, then at the bottom end of the list sit the molecules that are also found in healthy cells, perhaps just more widely expressed in tumor cells. And one of these molecules is CEA or CE125, molecules that we know of as markers for tumors, but that are also found, for example, in normal bowel cells for CEA. So, and then by degrees, the antigens can become different. So shared antigens, such as the MAGE family antigens, viral antigens, and then the neoepitopes that I already mentioned. And this is really important because, of course, when you think about it, our immune system is really geared to ignore the stuff that's self. And is really good at picking up the stuff that is new and different. So these neoepitopes and the viral antigens. So you would have thought that if you wanted to make an immune response or make a vaccine, then these would be the key targets that you might want to choose, because this built-in control of not allowing immune responses to occur against what is in our healthy cells is really hardwired into the system. And our thymus, so this gland behind the breastbone, I always like to use the image, the T cells go to school here and are trained against the curriculum of self-antigens, and they're only allowed to leave the school and to graduate to being able to travel in the bloodstream if they're not reactive to self-antigens. So a long-standing puzzle has been whether these might actually not be visible to T cells at all, because of this process of central tolerance. More recently, however, it's become clear that there are exceptions to this rule, and there is a repertoire of available cells, but they are of lower affinity. So in other words, they're less good killers, if you were to phrase it in this way. So the question is now being reopened, which antigens actually can be exploited, which are most immunogenic. And we know that, as a net summary, these T cells clearly exist, because when you look under the microscope, they are present. So moving away just from the antigens that are on the tumor cells, I think, and that these are the tumor cells here, then the tumor itself in its totality is made of course, not just of tumor cells, but lots of other stuff is going on in parallel. And so the fibroblasts, for example, give the structural integrity to the tumor. And when we have fibrotic disease, also cause some of the adverse events that the tumors mediate in the patient. But there are lots of other cells in there also. So macrophages, dendritic cells, myeloid cells such as neutrophils, and of course my favorite guy is the immune cells, the T cells in particular, and these come again in multiple different flavors. And I've already mentioned the blood vessels that are formed and may again be susceptible to immune attack. So if we then sort of break this down into compartments, then today I really would like to focus on the CD4 T cells, and specifically on those cells that have regulatory capacity, because I think it is becoming clear that all antigens that are in the tumor can both activate effector cells, CD8 and CD4, but also, as part of the way our immune system works, induce a regulatory component. And as we're beginning to be able to quantify the relative contribution of these components, it's becoming clear that we really need to think about how to remove and inhibit regulatory cells. So then if we think about this from a developmental perspective, the cells that come out of the bone marrow have left school, i.e. the thymus, that have gone into circulation. They're initially not very good at recognizing antigens. So there's lots of them, and they're in their naive state, not very effective. So they need to be trained and turned on. And in this process of training, you select out those cells that are better at recognizing whatever the problem is. So that could be flu or coronavirus or indeed tumor. And we now know that the best cells have this feature of tissue residency in the CD8 compartment. Tissue residency means they sit in the tissue and don't recirculate. But in the other parallel development, the same tumor antigens also, as I've already said, activate regulatory cells. And these Tregs, or regulatory T cells, come out of the thymus also, so they are also trained. This time they're allowed to leave the thymus if they see self-antigens, because they provide a developed brake, if you wish, for inhibiting these cells if they've done their job or if they're of the right flavor. And therefore, there is another parallel development of adaptive immune responses that leads from regulatory cells that are initially lowly suppressive, stimulated by antigen, and that are increasingly more highly selective. And the particular phenotype of these cells are these follicular regulatory cells that I'll speak about quite a bit. And of course, the tumors don't invent new immunology, that just take advantage of pathways, structures, mechanisms that are also relevant for our normal immune responses. And therefore, they simply subvert individual features of the immune system. So what I've drawn here is a germinal center. A germinal center is the place where all these interactions between antigen, dendritic cells, and T cells initially start off. And of course, the most prominent places where we have germinal centers are our lymph nodes, the spleen. But then lymph nodes are distinct structures, and many of our organs have these not anatomically limited structures called tertiary lymphatic structures. And it turns out that these are the places where you have your T cell engage with your B cell, and the B cell is helped in order to become a plasma cell, make antibody, and to become a memory B cell. And these are the helper cells, or the T follicular helper cells, that, because they live in the follicles, help the B cells to do their job. But in parallel, regulatory cells also play a role, and when they sit in the germinal center and have the features that keep them there, and then become T follicular regulatory cells. So these cells don't help B cell responses, but they limit B cell responses. And there's quite an intriguing data set that these cells may actually kill B cells that are trying to develop. So fast forward and think about this in a tumor setting, then if the structure is now trying to make immune cells against the tumor, then these cells will be useful for the patient in turning on anti-tumor immunity, and these cells will be bad for the patient in turning on anti-tumor immunity. And we also know that these cells make lots of PD-1. And when we first started examining the lung cancer and then head and neck cancer and then other data sets that were becoming published in the single cell analysis that people were reporting, it turned out that this population just hadn't been recognized. And they're really actually quite common, these T follicular regulatory cells. So when we looked in this population, this is a single cell analysis. Each individual dot is a cell, and I've colored the ones that have this regulatory phenotype. The shorthand for regulatory T cells is the expression of a transcription factor, which is called FOXP3. So you could say Tregs or FOXP3 positive cells, and by and large, you would talk about the same thing. Now, if you look at these FOXP3 positive cells in the single cell data sets, these are all the published data pulled together. Then in melanoma, in non-small cell lung cancer, head and neck cancer, breast cancer, colorectal cancer, liver cancer. So I think that our perception is generically there are lots of these FOXP3 positive cells that are in the CD4 gate of T cells from tumors that are of this follicular regulatory cell type. So suggesting that from the published data and our own data, these cells actually are abundant in many solid tumors. And so they have an intriguing role, not just because they are inhibitory cells, but because they also express a lot of PD-1. And if you look at them on a sort of per cell basis and ask the activated CD8 T cells, how much PD-1 do they make, and the follicular regulatory cells, how much PD-1 do they make, then these cells on a per cell basis make the largest amount of PD-1 in the tumor microenvironment. So then if you think about that a little bit further and you think about giving these patients an anti-PD-1 antibody, then there are a number of consequences that we propose. So one of them is, of course, it soaks up the anti-PD-1 antibody. So if the antibody is trying to get into the tumor and to activate T cells, and you've got a sink of cells that is taking up the antibody, then you would have less available to release your effector T cells. And we know that access of antibodies to tumors is a real issue. So this may actually be a significant problem. In parallel, however, the anti-PD-1 antibody will also unblock these inhibitory cells. So they will begin to divide, they will accumulate, and they will become active, and they're really good inhibitory cells. So the net result then is that you're releasing and turning on an inhibitory cell population that is competing for attention with the effector cell population that you actually want to control the tumor. And so this is, I think, one of the concepts by which these regulatory and specifically follicular regulatory cells are becoming really important in the way we think about cancer immunotherapy. So then I think that if you now look at this immunotherapy puzzle under this particular lens, then you would be able to assert that this cell type contributes to the low efficacy. And for example, if you had lots of regulatory cells, you would have thought that the anti-PD-1 antibody will be a bad thing for the patient because they will activate inhibitory cells. And we're just trying to work out on a large cohort of head and neck cancer patients in the first instance, whether we can define thresholds of what is a good ratio and what is a bad ratio, and then prospectively look whether that informs whether immunotherapy with anti-PD-1 can be predicted to be good or bad for the patient. So this is a sort of watch this space, we'll work with our pathologists kind of project. But we know that if you take these cells out, these regulatory cells, for example, with an anti-CTLA-4 antibody, then you also take out the same regulatory cells that are, for example, living in the bowel. And that I think is one of the reasons why we get immune-related toxicity. So the same mechanisms that would remove inhibitory cells or indeed activate inhibitory cells in the tumor microenvironment will also be applicable, for example, in this bowel or in the skin or in the lung or indeed in the heart. And so we think that the immune-related toxicity then becomes linked to the yin and yang, to the effect of, to the balance of effector cells and the balance of inhibitory cells, and then the pattern of adverse events becomes dependent on which cell population you're preferentially activating. So by assertion, then you would think that if you have an anti-PD-1 antibody and you activate inhibitory cells, then you probably won't get very much toxicity, but you might also not get very much benefit. And we know that in clinical practice, only a small percentage of patients develop significant immune-related toxicity from anti-PD-1 antibodies. But if you use a drug that removes the Tregs or T follicular regulatory cells, for example, also from the bowel, then you would get colitis and dermatitis. And that is an area that we're investigating very proactively, and we hope to work with the stuff that Anna has set up to get access to tissue to look at this practically. So if we focus back out and think about regulatory cells, then we're beginning to define T follicular regulatory cells as novel cellular targets for immunotherapy. And I think most of this I've already said. Tregs are responsive to anti-PD-1 treatment, present in every organ, prevalent in many tumor types. And the problem is that our current drugs don't really selectively affect cellular compartments, and we're working really hard on trying to set up an antibody production process in which we might pick some of the differentially expressed targets for selectively removing these regulatory cells. And indeed, when we look at the work that has gone on in the past, trying to remove regulatory cells, then a lot has been done, and much of which has not been very effective. So the earliest attempts were with a small molecule, so cyclophosphamide, which was thought to take out Tregs in the tissue. And you may all have come across studies where cyclophosphamide has been given as a tool to improve immunotherapy, really not with much clinical effect. Lots of antibodies have been in the clinic, so anti-CCR8 antibodies, anti-ICOS antibodies, anti-CD25 antibodies, and most of these have not really performed, either because they don't work very well, maybe because of the targeting, or because they also cause immune-related toxicity, and that's because the same molecules are upregulated on Tregs in the bowel or the skin, as well as in the tumor. So at the moment, we don't really have compounds that get rid of one and leave the other behind. And that is particularly true for anti-CTLA-4 antibodies, which are, I think, at the moment, the best targets or the best molecules we have to get rid of Tregs. And I hope to persuade you during the rest of this presentation that small molecule inhibitors of T-cell receptor signaling, so PI3 kinase delta inhibitors, may offer a pathway away from that. We know that preclinically, when you have animals that don't have Tregs, they all get really bad autoimmunity and die within 3 weeks. So getting rid of regulatory cells is a really bad idea. However, and these are data from our own lab, when you take out the follicular regulatory cells, these animals develop normally and often don't get autoimmunity, or if they do get it, in terms of mouse life, this is very late in life, after 30 weeks or onwards. And when we now begin looking at the overall literature and ask whether there is a role that would suggest that these follicular regulatory cells are important, then actually there are lots of hints in the literature. So, for example, B cells and removal of B cells and tertiary lymphatic structures clearly promote immunotherapy, effective for anti-PD-1. That's been looked at really nicely, and there are lots of other data sets that argue that these tertiary lymphatic structures in which these TFRs normally live are gatekeepers for effective immune responses and therefore by extension for effective immunotherapy. And this just compares at a molecular level similarities and differences between Tregs on the left and T follicular regulatory cells on the right. And I've picked out this box because we think that these might be targetable molecules that are particularly susceptible to targeting in regulatory cells that are of the follicular regulatory flavor. So activating ICOS antibodies, targets against antibodies against, sorry about the jumping back and forth, CD177, and we are very interested in this particular molecule. It's an IL-1 receptor 2, which is a decoy receptor only expressed on these regulatory cells.
77 is an integer. 77 is also odd and is not prime.
There you go. So that's Siri thinking I'm talking to it. I do apologize.
I'm not sure I understand.
Oh, for crying out loud. So we think that the possible ways of getting rid of regulatory cells would include antibodies, so by activation-dependent cell cytotoxicity, using selective inhibitors, and using variants on the way that people have already done with ICOS signaling. And what we found is that when you take our Tregs in this mouse model with an anti-CTLA-4 antibody, we are very able to get rid of these regulatory cells, both T follicular regulatory and normal Tregs. And here are the data. You can see that you really take down the percentage and the quantity of regulatory T cells if you treat these animals with an anti-CTLA-4 antibody. And specifically what happens is that in this model, which is a melanoma model, as well as a colorectal model, where anti-PD-1 on its own doesn't usually work so well, you can recover the immunotherapy control of the tumors by running with an anti-CTLA-4 antibody before giving the anti-PD-1. So this sequential therapy is the survival curves are demonstrated here, and you can see that the best control we can achieve in these animals is if you give an anti-CTLA-4 antibody, in this case a single dose, before giving the anti-PD-1 antibody, whereas anti-PD-1 on its own really doesn't work in this model at all. So this suggests that maybe this would be a really interesting way of reducing the toxicity of anti-CTLA-4 antibodies by giving a single dose before anti-PD-1. And it will be interesting to see whether we can find partners who want to do that with us clinically. This is our own data set looking at a historical cohort from Southampton, and these are the patients, and it's got all the usual caveats and limitations of historical data sets. And we just asked what would happen, or how was the outcome if we looked at the scheduling of the treatment. And of course, changes in treatment here in this cohort of an N of 270 or so were driven by disease progression. So initially anti-CTLA-4 and then anti-PD-1 gave us really good long-term responses, about 50% of patients. Whereas if we did the other way around, anti-PD-1 followed by anti-CTLA-4 was not able to recover a single patient. So suggesting that the ordering of these drugs might matter in melanoma. There are no similar data sets in other solid tumors that I know of. So I think in the end, it will probably have to be tested prospectively. So about 8 years ago, we started talking to a chap called Bart van Hazenbroek. So he's a scientist initially at that time in St. Bartholomew's Hospital, who described that downstream of the T cell receptor sits a signaling cascade, which through the PI3 kinase delta isoform P110 is able to lead to the consequences of T cell receptor signaling. So in other words, the T cell engages with its peptide in MHC class 1, say, and then the downstream result is that it leads to cell division, cell activation, and cell differentiation. And Bart was the person who identified that this particular subvariant or isoform of PI3 kinase delta is really important for T cells and B cells. And he put together a study that was published in Nature in 2014. In this study, he had, and his postdoc, who then went on to work for Amgen, demonstrated that if you had a tumor that was not susceptible to immune attack, you could convert these tumors into immune controlled by giving a PI3 kinase delta inhibitor. And they did this in a pancreatic model. And this conversation, actually a chance conversation with Bart, made us wonder whether we could take this into clinical testing. And that led to a clinical trial funded by Cancer Research UK, in which Liverpool made a major contribution. So Joe Sacco in Clatterbridge was the oncologist who drove the recruitment, and of course in collaboration with our head and neck surgeons, and Andrew, I think, is on the presentation this morning, who made this whole study possible. And then there are 3 partners in the La Jolla Institute of Immunology who then helped me and worked with me on the immunology: Vijay Anand, Simon Eschweiler, and Mitch Cronenberg, who's a gut immunobiologist. And so trying to take this idea into humans led to a randomized phase 2 study, a placebo-controlled study, in which we gave the compound, the PI3 kinase delta inhibitor, the shorthand is AMG 319 to patients before they underwent their head and neck cancer resection. So we did the patient was diagnosed, had a primary biopsy, got their neoadjuvant PI3 kinase delta inhibitor, and then went on to have a resection. We thought we'd be really smart, so we'd used a dose that had been established as the maximum tolerated dose in a lymphoma trial, and we made lots of people really unwell. So we were able to demonstrate that we were able to take out the regulatory T cells from the tumor microenvironment. So we removed the Tregs in the way that we had expected, and we also activated T cells. But what we learned was that when you did that in people, and here's the control group and here's the treatment group, you also caused the same biological effect in the bowel. In other words, we were causing Treg depletion in the bowel, and we're causing lots of immune-related adverse events because we were taking out the inhibitory population. And we were able to see the correlates of that in the blood. So we think that what happened was that we made the Tregs and the T follicular regulatory cell leave the blood and leave the tissue and go into the blood, and that was correlated with this increase in ICOS expressing, where ICOS is a molecule that tags activated regulatory cells. So you can see that the Tregs are increasing in the blood, both in number as well as in activity. And we think that this is the global effect of what is happening and is a correlate to this immunobiology in the patients. We didn't really connect enough material to be able to interrogate the why and how in the bowel. So we went back to a mouse model of, in this case, colitis, and we were able to demonstrate that regulatory T cells in the tumor and in the spleen were really quite different, and that when you looked at the Tregs in the bowel, the inhibitor turned on and turned off particular subsets of regulatory T cells. You can see that here, these are turned on and these ones are turned on also. They begin to expand, and the size of the dot means how many cells belong to the same clone. So a tiny little dot means a single cell, and these means clonally expanded cells. So the net result was that we were able to demonstrate that removal of the Tregs from the bowel activated T cells in the bowel and led to shifts in the regulatory cells in the bowel also. And that was correlated in the mouse with a really profound activation of an inflammatory phenotype that was exactly like we see in colitis after, for example, CTLA-4 treatment in humans. So really beginning to hang together the way in which the compound worked across species, and being able to model the immunobiology from the mouse and translating that back into the humans. What we, however, also saw is that this was a dosing effect. So when we gave placebo, then the tumors grew quite happily. But if you gave the continuous dosing, you achieved good tumor control. But when you gave the dose less frequently, and we looked at 3 different dosing schedules out of 7 days, so 2 days out of 7, 4 days out of 7, and every day, then we were able to retain anti-tumor control. But what was clear was that we didn't cause as much toxicity, or any toxicity at all, in the animals that were given intermittent dosing. So suggesting then that unlike antibodies, so anti-CTLA-4 antibodies, these drugs have a much more short-lived effect. It might be much better controllable, and therefore suggests that if we were to develop clinical testing with intermittent dosing, we might be able to get away without toxicity and yet retain the anti-tumor control. And that sort of summarizes where we stand at the moment. So we know now that cancers, if they are successful, they train regulatory T cells. So they offer another protection against the immune attack. And this is also true for the neoepitopes. There was a recent paper in Nature by a large collaborative group that demonstrated that even these neoepitope reactive T cells can have this same regulatory phenotype. And we also have shown that anti-PD-1 activates these cells. So then the step from there will be that removal of these Tregs will add clinical benefit. And I think the evidence that addition of anti-CTLA-4, for example, in melanoma to anti-PD-1 brings the response rate up to 50% from about 35 or so percent is a really strong case that this will work in humans. But of course, we know this is toxic and has a really limited applicability in humans. Other approaches have not yet been very successful or also cause toxicity. Lots of antibodies have been tested. We now propose that transient removal of these inhibitors from the tissue might offer a solution. And we are really intrigued by these PI3 kinase delta inhibitors, and indeed are just working on a clinical trial with one of these inhibitors called zandelisib, which is already in the clinic in lymphoma, and we want to take this into lung cancer as a run-in to anti-PD-1 treatment. And we've just been approached by Ionctura, who have a separate compound called IOA244 with a really remarkably benign toxicity profile. So we're really keen to try and understand whether this compound works in another way rather than by depleting regulatory cells, and how you might be able to sort of square the circle of no toxicity and apparently clinical effect. And so we're really excited about further developing this class of drugs, because I think they'll offer a window of opportunity into really improving response rates for some of the solid tumors that we are currently struggling with. And of course, this is, a large international collaborative effort with lots of partners in many places. And Terry was the reason I wound up in Liverpool. But the key players in the PI3 kinase delta trial were also Andrew and Richard Shaw and, of course, Joe, who have enabled us to do this study and get to this point in the first place. And with that, I would like to leave it, and thank you very much for your attention and take any questions. Okay, Shavita.
Hi, Christian. Very good talk. Really excellent. Because in the brain cancers, as you know, all the immunotherapy hasn't shown any results. Like there are 6 international failed trials. Do you think, is there any and I'm not sure on that. Is there any work done, do you know, on these TFR cells, or do you think that could be the answer there? And if yes, is there any plans to expand the research to include the neuro-oncology?
So we have a data set in children's brain tumors. So this is with a collaboration with the pediatric hospital in San Diego. Okay. And indeed, the principles are the same. So neoepitope reactive T cells exist. They are constrained by anti-PD-1, and regulatory cells play a role. We don't have any data in adult brain tumors. And I've approached Mike Jenkinson here in the Walton Center to see whether he would be interested in exploring this. And if you were interested in coming to the table and me coming to the party, we'd love to have that conversation with you. So I think what we need is say, a set of 20, say, glioblastomas and do the single cell analytics. The tools are now very well established, and we can just, if they have material, we can just do it. So the issue then is in the appropriate sample collection and getting enough material. And yes, it would be really exciting to do just that.
Okay, I think we should have a talk maybe outside this meeting, and but that's I'll be really interested in, because that's something I would definitely like to work on.
Brilliant, fantastic.
Thank you.
I've achieved my aim. Any other questions? Doesn't look like it. Oh, hold on. I'm very bad at doing this sort of managing and talking at the same time. It doesn't look as though there are any other questions.
Sorry, Christian. I entirely agree. Doing a talk and trying to manage these click boxes in on a team meeting is virtually impossible. So it's Isabel. Thank you. It was great, really interesting. So what tumors do you think this strategy would be most successful? Because clearly they're not all the same. Some respond much better to immunotherapy than others. Maybe this strategy would be particularly useful for tumors who do not respond to immunotherapy measures. You know, like in prostate cancer, been lots of clinical trials. Sort of, I think the principle was, well, it works in some else's. We've got lots of patients. Let's just give it a go and combine X with Y without really much thought whether it would do any good whatsoever, as far as I can see.
So I think that the role of Tregs is wherever there is antigen, Tregs will be trained, and that is true for cancers as much as any other tissue. So my expectation is that this will be particularly relevant where the balance between the regulatory and the effector cells is wrong. And we're just trying to work out, what would be the threshold, say, in lung and head and neck cancer of a good balance versus a bad balance. We haven't worked that out yet. And I think if you had tumors that have no immune cells, then there will also not be any Tregs or any T follicular regulatory cells. So I think it is pretty clear to me that in that group of patients, getting rid of Tregs is unlikely to work. So it'll be in tumors with some or maybe many T cells where the balance happens to be wrong. And I think our prediction from the data we hold is that will be about 30% of the solid tumors. So those, I think, will be patients that don't respond to anti-PD-1 treatment, but that might be rescued by Treg depletion or TFR depletion. The second puzzle where this will play a role is if you want to vaccinate against tumors. So we know that if you vaccinate, particularly if you use whole antigens, that you will also turn on regulatory cells. So I think that some of the failures of vaccination is not because the vaccines didn't work. They just turned on the wrong cells, and that led to the net result of no benefit. So we'll be looking at this preclinically in again, of course, in a mouse model. But my expectation is that if you have a self-antigen or indeed a neoepitope vaccine, and you vaccinate against that, then you will turn on T cells that recognize the antigens, and the clinical result will depend on the balance of what you turn on. So if you turn on similar numbers of inhibitory cells as effector cells, then nothing useful will happen clinically. If you turn on lots of effector cells, then the tumor gets better. And if you turn off on lots of regulatory cells, tumor gets worse. And actually, there are examples in the literature of all three of these outcomes now. So again, I think, and what we're just in the process of doing is beginning to ask whether, say, in lung cancer or head and neck cancer, if you look at all the T cells in the tumor, can you then take particular molecules, and we'll start with one of the shared antigens and a set of neoepitopes. Can you identify what the balance is for particular antigens? So this group from that published in Nature 3 weeks ago, Oliveira was the first author, looked in 5 patients with melanoma and found that the neoepitope reactive cells were split into regulatory and effector cells. So you would predict then that the patient with more regulatory cells will not respond to a vaccine, and probably also not benefit from anti-PD-1, and that you would need an anti-CD4 antibody to remove those. And that's, I think, the direction of travel. So apologies, long answer. I think we'll be able to add about 25 to 30% of responders in tumors that are not completely devoid of T cells. And I think this will play a major role for making vaccines clinically effective.
Yeah, I presume the advantage is you would tailor your treatment more rather than a sort of one fits all and then hope for the best, when that's essentially what we do in the clinic in the moment.
Yeah.
It was something which may just be a more effective strategy. I mean, these drugs by any means are expensive and are very expensive. So, from this sort of strategy, and like you say, the toxicity can be very significant.
Yes, and I think
so a strategy to tailor it towards the cancer dash avoid toxicity would presumably a more beneficial approach than what we do right now.
Absolutely. And I think, you know, when the only choice you have to make is to give anti-PD-1 or not, then it's relatively straightforward, isn't it? You give it when you can afford it. But if there are multiple options, and then you need to know how you're going to make choices. And that's, I think, where this data is going to help. These data are going to help.
Mm. The other thing you said, you know, about the PSMA antigens, I mean, clearly it's, I mean, this trial with lutetium-177, which is a radioactive tracer and is used as a therapeutic kind of target, the PSMA. I mean, and they have shown it works, even in patients with multiple pre-treatments and so on. But it is clearly a major problem to give because it's radioactive and you have all the radiation protection issues, which are massive, and it's also very expensive. To the point that there's still debate with NICE of what confidential rebate they need to get the license, which normally means it is expensive.
Yes.
So is there any other way of targeting PSMA?
Yes, I think T-cell attack is the way to go. And so antibodies to PSMA as a therapeutic haven't worked. As a vehicle for delivering radioactivity, yes, they have worked, and that's what you're just referring to. I'm very interested in PSMA as a T-cell target. In prostate cancer, it is highly upregulated on the vast majority of prostate cancers. So it would be a really good T-cell target. In lung cancer, for example, it's highly upregulated on the neovasculature, but not on the tumor cells. So it could be considered as a target for vascular anti-angiogenic vaccination, highly selective for the tumor because normal blood vessels don't make this molecule. It's not quite clear why that is, but that is at least the observation. So I think what the key bit for prostate cancer is to understand why does immunotherapy not work, given that there are such highly selective molecules like PSA, PSCA, PSMA, prostate acid phosphatase, all of which would be really well targetable. And why does that only work in such a small amount? And I think, again, I predict that the puzzle will be to some degree in these regulatory cells, and it would be very nice to look.
Great. I think we'll have a discussion outside the meeting as you're nearly done with your time.
So, you know, but it isn't unreasonable to look because the tools are going to be generic. So, you know, whether you do multiplex immunohistochemistry for prostate cancer as opposed to lung cancer or head and neck cancer is really neither here nor there, because all the difficulties in the development of the assay, but then it becomes modular and you can apply it to anything that people are interested in. I apologize. I've taken much longer than I was supposed to. So thank you so much for listening. Isabel and Shavita, thank you for your questions. I look forward to discussing this further, and I wish you a quiet Friday and a wonderful weekend. Goodbye.
Bye.